Today we'll show you some of the tools that are being developed here at BSC for performance analysis of parallel applications. I hope you can hear me well over Zoom.
Yes, perfect.
Thank you. And the plan for this session is I will show you some slides first, and then we will move to the fun part where Lau will show you how to get a trace with Extrae and to do analysis with Paraver for a pure MPI case and a hybrid MPI plus OpenMP application. But before we talk about applications and performance and clusters and MPI and all that, let's talk just for a minute about ourselves, about humans. And here, I have 3 examples on why we are so good working with images. Have you seen this movie? I have. I have also read the books. And the last time I saw the movie, it was a marathon in the cinema, and I was sitting for 10 hours in a row looking at this. It was quite literally a pain in the ass. But going through the books, it took me days and weeks, and they were able to squeeze a huge amount of information in just a few hours that I was able to digest just by sitting there like a zombie and looking at it. And this is because we are extremely good at processing information and obtaining information that comes visually. Another example could be infographics, which are very trendy right now in the work environment. And it is not because the plots are very pretty, it's because they convey a lot of direct and very synthesized information in a very effective way, much more than reading pages of a report. And the last example that I have is more like a game, a quick experiment, because we are extremely good at identifying things in images. And if I show you this, the moon, a rock, a cloud, what do you see in these images? Do you see anything in common in these images? At this point, many people start to see rabbits, and none of them is a real rabbit, and they are in different materials, different scenarios. And if you didn't see them at first, now that I've told you, you can't stop seeing them. And this happens automatically in your brain. It's like a game. So the question is, can we use the power of our brain to work with images to do performance analysis? And the answer is yes. What we have to do is to express performance as images and then identify those shapes that express good performance or bad performance. So this is the idea of our tools that we have been developing for, well, more than 30 years now, which means a couple of things. The first one, bad news for me, is that we are getting old. The second one is that we must be doing something good, because the same design principles of flexibility and adaptability that we started applying so long ago are still valid now that the applications are becoming much more complex, that the hardware is becoming much more complex, that the software is increasing in the number of layers, parallelization, and altogether we are still able to obtain performance data in high detail and successfully navigate it and get insight from it. Our tools are based on traces. They are open source. You can get them from the website. And the main tools that we'll be seeing today are 3. One is Extrae. Extrae is the instrumentation framework. This is like the video camera that records what is happening during an execution. Then Paraver, which is the trace visualizer. This is like the video player that plays the trace again, so you can see and record and browse through the data. And then DMMAS, which is a simulator that was originally designed for MPI applications, but now has been extended to also cover OpenMP and CUDA. Then one characteristic that makes our tools a bit different to others is that we focus on the dynamic behavior rather than the syntactic structure. What does this mean? So for example, if we have 2 functions in the code that behave very similarly, we focus on this common behavior rather on each of the functions. So when we assess that there is a performance problem and we have a suggestion to make, we then pinpoint to all the points in the code where this happens. Or a different example, imagine we have a multimodal function that, depending on the parameters that you pass to it, this function has a conditional in the middle, and sometimes you go through the if and sometimes you go through the else. And so the behavior of the 2 branches is very different. If you take all the invocations of this function together and make an average, maybe this average doesn't mean anything, because sometimes the function goes through the if, and that is very expensive, and sometimes it goes through the else, and that is very quick. And the average doesn't really measure that reality. So what we focus on is that there are two behaviors. And then we have mechanisms to pinpoint those two behaviors back to the same function. Let's start with Paraver, although Paraver is not the first step. The first step is Extrae, which is the tool that captures events of what happened during the execution and record them into a trace file. The Paraver trace file looks like this. It's a very simple format. It's ASCII, it's open, very easy to generate, and it records time-stamped events, and these events are represented by two numbers, a type and a value, integer numbers. And it is very easy to process, manipulate, so it's easy to script something that manipulates the data, so you can incorporate those scripts into a workflow to process the traces. From the data that is contained in the trace, we draw mainly two types of views. You were introduced to this the other day already. One is the timelines, but as a quick recap, on the vertical axis, what we have are the objects, in this case, MPI ranks. On the horizontal axis, we have the time, and then the colors in the timeline indicate what are these objects doing over time. On top of the timelines, we also have tables. It can be profiles or histograms, and then we have mechanisms to navigate from the timelines to the tables and back from the tables to the timelines. Okay, we'll see that later. We also have mechanisms. Yes, it goes with delay. We also have mechanisms to manipulate the data in the trace and reduce it, and select subsets of information, and then generate smaller traces that only contain that small set of information. Okay, and those smaller traces can be again opened with Paraver and browsed and analyzed and further filtered. And the main two goals of this tool, one is to be very flexible. And so we use it to analyze the performance of parallel applications, but we could use it to analyze the evolution in the price of the oranges in the market. So for Paraver, the data that is contained in the trace is completely agnostic to it. It doesn't matter. And with the tool, you can compute any metric that you want with the data that is present in the trace. And so Paraver works somehow like an equation builder that allows you to select which are the operands to build any formula that you want with the data that is present. And the second main goal is to facilitate comparative analysis, because in most cases, it's not only about looking at one case and that's it. In many cases, you have to do one run, see what happens, tweak something, change something, make another run, scale, and see what works best. So the tool comes with many mechanisms to load multiple traces and synchronize them and facilitate this comparison. As I was saying, there are two main types of views. You were also introduced to this the other day, but as a quick recap, the first one are the timelines. And with the timelines, we can render two types of metrics. One are the categorical metrics, like, for example, the MPI calls, which means that the MPI calls are limited. Okay, and because they are limited, what we can do is to assign one identifier to each of them. And this identifier is rendered with a distinguishing color, with a different color. Then I was saying, we have mechanisms to go from the timelines to the table. So there is a button, and when you click it, you get a profile. Okay, and then for every color in this timeline, you get a column in that profile. In this table, we compute different statistics. By default is the percentage of time, but also the total aggregated time, average duration, number of calls, and more. Then the colors in these cells over here indicate the intensity of the metric. Okay, so when you see blue, that means high value of the metric, in this case of time percentage. Then at the bottom of the table, you'll see that there are some average statistics, and these are very important because they allow to compute the efficiency metrics. You will see that later also. And then at the beginning, I was saying that we are very good at working with images and that we like to work with images. And there is a bunch of numbers already here. So there is a button that you click, and this zooms out, and you don't see the numbers anymore. You only see the colors. But in here, you already can identify patterns. Okay, you can see that the highest value of the metric is on the first column. Okay, so you can hover with the mouse in this first column and then see, okay, this is outside MPI. Okay, so most of the time of this execution is doing useful work, which is what we want. So that's good. Then when we want to look at continuous metrics, like for example, the number of instructions, okay, the number of instructions can go from 0 to infinite. To render this, we use a gradient, and the gradients in Paraver go from green to blue. Green for low values, blue for high values. Then in this timeline here, we are depicting a different metric, which we call the useful duration, which is very useful. Okay, this is the duration of the computations. Being a computation, anything that happens between two calls to the parallel runtime. So when you see blue, that means there is a long computation. When you see green, that means it's a short computation. And with this view, we use it a lot because it is very useful to identify structure. Now, with a quick glance, here you can count and see 1, 2, 3, 4, 5, 6, 7, 8, 9 iterations, which are characterized by that they start with a long computing phase, followed by a short one. And this pattern repeats. Now, when you click on the same button as before, now we get a histogram. And the way to read the histogram is very similar. On the vertical axis, we have the MPI objects or threads. In this case, it's MPI ranks. And on the horizontal axis, we don't have time anymore. What we have is bins of the metric. In this case, the metric is the duration of the computations. So when we are on the left of the histogram, we have short computations. When we are on the right of the histogram, we have long computations. So this straight green line over here is telling us that all processes are doing short computations. When? We don't know. This doesn't tell the histogram because the histogram doesn't have time component. It aggregates all instances of computations throughout the whole execution. To know when, we have to correlate with the timeline. So these short computations happen to be the ones that in the timeline we see in green over here. When we look at the right of the histogram, now this wavy shape over here, it is telling all processes are doing long computations, but some are taking less time, and some more, and some less, and some more. So this kind of wavy shapes are a warning red flag that not all the processes are behaving the same. Okay, where is this happening? Yeah, we don't know. We have to look at the timeline. Okay, and this actually corresponds to the blue phases. That you could already identify in the timeline this imbalance, because when you look at the blue phase, you see different shades of blue that happen simultaneously. And this is already telling, okay, some processes are shorter than others. Okay, so the ones that take more time are the ones that finish later. The ones that are faster are the ones that reach this black gap sooner. Okay, and this black gap is time that is paid in MPI. These enter MPI and they fill time waiting for the partners to be ready. This is actually an example of a real application that was analyzed years ago. It was SpecFem 3D. And the story was that the developers had the idea of implementing asynchronous communications to improve their application. Okay, so when we analyzed it, we saw this huge imbalance in the duration of the computations. Okay, and so the duration of the computations has little to do with asynchronous communications. So we investigated this, and so what can be the reason to have imbalance in the duration of the computations? And the first reason that comes to mind is that the work is imbalanced. We can check that with the number of instructions. So when we look at the number of instructions executed, we see there are processes that do less instructions, more instructions, less and more and less. But the shape of this imbalance is not exactly the shape of this one. And this is telling, okay, there is a component of work imbalance, but there is something else. What can be something else? So maybe the system is not able to deliver constant performance. And this we can see with the IPC. When we look at the IPC, again, we see processes with less IPC, more IPC, less and more and less and more. And so it is the combination of these two factors which is resulting in this imbalance in the duration of the computations. And what is the typical reason to have imbalance in the IPC? in many cases, is the access to data that we can check with hardware functions, like, for example, the L2-miss ratio. In this case, what we saw, that again, there is variability in this, and so especially the bottom ranks are having a higher ratio of L2-miss or L2 misses. So the recommendation that we gave to them, there is a problem accessing to the data, which is causing perturbations in IPC. And on the other side, there is a problem in balancing the work per process. And with this recommendation, they went back home, and a few months later, they came back with a new version of the code where the work was perfectly balanced among the MPI ranks. They changed the data access pattern, so there were things started to fit in cache, and they managed to reduce the cache misses, and this resulted in the IPC being much more constant. The takeaway of this example is that it is very important to focus where it matters, because the initial idea was to change the implementation of MPI to use asynchronous communication, but that was not the problem. So we have to know what the problem really is. But sometimes these perturbations and variabilities are not so easy to identify. And this is another example of SESM. This is a simulator of different systems of the Earth, like the atmosphere, the ocean, and several of those. And in this example, we were simulating 2 full days on Earth. When we look at the histogram of the computations, you can see that there is a lot of variability. Okay, there's a lot of dispersed data, but not a clear shape like in the previous example. As I mentioned, we have mechanisms to go from the timelines to the tables, and also from the tables back to the timelines. Okay, so when we have this histogram, we can look at the timeline that produced this histogram. Okay, and when we look at it, it's very difficult to see something. Okay, for those with keen eye on Paraver, you're going to start to see some bluish shapes here and there, but it's not so clear. Now, using those mechanisms to navigate from one view to the other, what we can do is to select subsets of information. And so there is a button, you zoom over that area, and what this does is to focus only on these behaviors over here, which means to focus on the long computations, because we are on the right side of the histogram. Okay, and then we get a timeline that only shows those behaviors and filters out the smallest computations. When you look at this, now it's easier to see something. You see these blue clouds over here that repeat over here, and then another one over here that repeats over there. If you zoom on a small interval at the beginning of the execution, what you can see is that it's the top ranks, the ones that are taking longer. But if you zoom later on, you see that this behavior is the opposite. And now it's the bottom ranks, the one are taking longer. What was happening here? So we are simulating the Earth. Okay, so we split the work, and there are processes that are working on an area that is in daytime, and there are processes that are working on a different area which is in nighttime. Because of the models that were being simulated, it was more expensive to compute day than night. But as time goes by in the simulation, those that were in day are now at night, and vice versa. So this behavior keeps changing. Now, if you take this 2-day simulation as a whole, everything is perfectly balanced, because everyone spent the same amount of hours in day and night. So all the processes did exactly the same amount of work. But when you zoom in and look into the details, you see that there was variability everywhere. And this is the first answer to the question of why it is important to use traces, because it is important to have mechanisms to identify this low-level variability that is hiding. But then working with traces, there's many things to balance and some trade-offs that you have to make at different layers. The first one is, what do you measure? What we can measure is, for example, data at instrumentation points. Okay, this means capturing data at known points in the execution. For example, whenever the application calls MPI, we capture data at the entry and at the exit of the MPI code. We can also use sampling. Sampling, as you know, is to take random measurements that can fall anywhere. But then, regardless of the mechanism that you use, it will depend on the granularity of the application calling MPI, that you will have many many points where you capture data, or depending on the sampling frequency that you will have many samples or not, and depending on how many information you are able to collect, you will be very accurate or have a lot of overhead. To this regard, Extrae by default captures data at instrumentation points, like at the entry and exit of the MPI calls, but on top of that, we can activate also sampling mechanisms. Then there's trade-offs in the storage. You know, if we store everything that we collect, typically we are generating a trace. If we summarize while we collect, typically we are going to generate a profile. So by default, Extrae collects traces, but it also has some mechanisms to store profiled data, like software counters, face profiles, and also even tracing modes that generate a trace, but that is summarized by only capturing the long computing phases. And then to inspect this data, typically when you have a trace, you look at it with timelines. When you have a profile, you look at it with tables and look at the statistics. And then in Paraver, we have both mechanisms to navigate through the timelines, but also to compute the statistics on top of the timelines that we can inspect with tables and with numbers. The elephant in the room is that to obtain highly detailed traces, the size can grow quite large, quite fast, and this can be daunting in some cases. Okay, but worry not, because this is not necessarily a problem. Okay, the tool also comes with many mechanisms to filter and to manipulate the data. And here I have an example of CP2K run with 1,000 processes. It was 1 minute run, and it generated 60 gigabytes. Okay, so 60 gigabytes per minute is quite a huge amount of data. But then we have a filtering tool that allows to focus only on those long computations that are longer than this threshold. Okay, and just by doing that, we still see the full 1 minute of the execution, but only looking at the computing phases, and the size goes down to less than 400 megabytes. And then by looking at this, you can already identify structure. You see the initialization phase, then 1, 2, 3, 4, 5, 6 steps, and the finalization. Okay, because these 6 steps are very similar, we can focus on one, and then cut this trace only for this time interval, and then we can increase the filter to a finer grain resolution. And now we are looking at an even smaller computations. Okay, but doing that, the trace goes down to less than 200 megabytes. But now we are looking just at 10 seconds of the execution. And here, what do we uncover? That inside this outer loop, there is an inner loop with a pattern that also repeats. So what we can do is to keep zooming in and select one representative of this inner behavior, cut this trace, and now we are looking at a small interval of 400 milliseconds, but this cut, we do it from the original trace that contains all the data. So for this small time interval, we have everything, the MPI codes, the hardware counters, the callers. So this really tiny region is fully characterized. And so these mechanisms of filtering and cutting gives us this dynamic range of information that we go from the overall structure to the really tiny details. And having this is very important, and I have an example of a real case where we detected that one process was perturbed, okay, and it suffered from a preemption. And this only happened to one process, but when we look at the computing regions and at the MPI calls around this point, this is what we see, that everyone was perturbed. Why is that? Because this perturbation travels through the communication pattern, okay? Because this process that was delayed, if someone was waiting for him to communicate, those are perturbed as well. And when we zoom in this communication phase, what we see is that it ends with a collective. And the collectives have the superpower of absorbing imbalance. Okay, so some processes reach the collective sooner, some others reach it later, but then when they are all there, they are synchronized and then they continue. But if this collective was not here, this perturbation would continue along the next iterations as well, depending on the communication pattern, which is this example over here. In this case, we detected two processes being affected in the same node. So this is the node. These two processes fall on this red node. When we look at the MPI calls, what do we see? that all this area has been perturbed, okay? And this is affecting the neighboring nodes, okay? Because this process over here generated a dependency chain internal to the node and then to the neighboring nodes. What happens in the real case? The real case, the full execution, what we were seeing is that there were areas not especially perturbed, but that there were areas very perturbed. Okay, and then using the mechanisms that have Paraver to highlight outliers, you can pinpoint this. It's a bit difficult to see because of the colors, but these are orange bars, which is highlighting the largest ones, okay? And these ones were much larger than expected. So what is really important is to have these mechanisms to identify these microscopic effects that in reality have a very large global impact. Now let's switch to BMS. Okay, so change story. BMS is a simulator. The idea is to be a very fast simulator, not a super precise one, that gives you trends. So if I had a faster network, which is twice as fast, what would happen with my application? Stays the same, it improves, more or less how much, okay? Initially, it was designed for MPI applications. Now it also supports that these applications contain OpenMP and CUDA. And DMS, what it simulates is a very simple model, okay, that comprises a cluster of nodes that contain CPUs. Then the communications within the node go through memory, and the communications to other nodes go through a network, which is characterized by two parameters, which is the number of buses and the bandwidth. And the connectivity of the nodes to this network is characterized by other two parameters, which is the number of links and the latency. So with this simple model, what are the types of studies that we do? One is the parametric sweeps. I have an example of it. Here we were comparing two implementations of the same code. The code was WRF, and it had two versions named NMM and ARW. So we were comparing these two implementations running 3 different scales of the problem. Okay, so 6 experiments in total. Now, what we are testing are different bandwidths. So starting with this point over here, which was the highest bandwidth of all, you see that this is the baseline, and then we start to reduce the bandwidth. So as we move to the left, you can see that there are 3 lines that start to fall very quickly. And these 3 lines all happen to be of the ARW version. And this is telling this version of the code is more sensitive to bandwidth limitations. So if you start to reduce the bandwidth, this code is very sensitive and the efficiency will drop quickly. Whereas the other 3 lines are able to stay on top of the plot, which means it's more efficient, meaning that this other version of the code, NMM, is more resilient to bandwidth limitation. The other type of analysis that we do is what-if analysis. What if I had a faster network? What if I had more latency, simulating that the software stack is more expensive? I will show you an example right now of this. And a very important message is that Paraver and DMS work together. Okay? The input for DMS is a Paraver trace. And the output of DMS is a simulated trace that can also be loaded with Paraver and inspected in detail. Then in Paraver, you have the real run and the simulated run, and you can compare them with detail. This is an example of what-if analysis. Here we have an MPI application with 2 phases. The first phase is doing collective operations, and the second phase is doing peer-to-peer. Okay, the peer-to-peer is represented by these yellow lines. All right, the sender and receiver. So what if we increased the latency by 3 orders of magnitude? Okay, which would mean that the MPI layer, that the MPI library is more expensive, more inefficient. So nothing happens. The simulated run and the real run look like the same. What happens to this code if we decrease the bandwidth? So for the first half of the execution, for the collective phase, there is no impact. But then from this point on, the second phase, the peer-to-peer phase, this one is impacted very much. And if you look at the lines, everyone is sending upwards. So they are doing some kind of reduction with peer-to-peer communications where everybody is sending to the same guys. Okay, and so these same guys are getting saturated. Okay, so this part is affected. Okay, this is an example of what-if analysis. Now, if you remember the first example of all, where I said that the developers of Spectrum 3D came and they were asking, they had this idea of implementing asynchronous communications, but we told them that was not the problem. The problem is the imbalance in the computations. The real answer to that question was given with DMMAS, actually. Because with DMMAS, we can simulate an ideal network. An ideal network means with infinite bandwidth and zero latency, which means that the communications would be instantaneous. Okay, so if you simulate this ideal network and your application does not improve, which is what happened here, this is the real run, and this is the ideal simulation. This is telling you your problem is not in the communications. Okay, so this is what gave the real answer to their idea of changing the implementation. But even if the application does not improve, we can validate what happens if we decrease the bandwidth, for example. So we started to do that, and we decrease the bandwidth to 100 megabytes, nothing happens, 10 megabytes, nothing happens. At 5 megabytes, you start to see something, but you really have to go really, really down to 1 megabyte to really see a perturbation. So in this case, this application, the bottleneck is not in the communication, so don't worry about that, because that is not your problem. And I have just introduced this idea of the ideal machine, okay, with an ideal network of infinite bandwidth and zero latency. If we were able to build that, one would expect that all the communications go away because they would be instantaneous. And so here I have an example of gadget. Okay, each color here is a different MPI call. When you simulate this ideal network, the execution indeed improves, but you still see many colors, many MPIs. So why didn't go away? What happens here is that not all MPI time is due to transference of data. In MPI, you also pay the dependency chains, okay, as in the previous example that we saw. So if I want to communicate with you, but you are not ready, and this is a synchronous communication, then I have to wait for you to be ready. And when we both are, then the communication happens. But this first time where I'm just waiting for you is paid in MPI. And this does not improve because of having a faster network. This only improves if you fix the imbalance that is prior to this point that makes us reach at different speeds. And this is what simulating this ideal network highlights, this intrinsic behavior of applications when they are unbalanced. Is it important? Very important, because if you cannot improve in an ideal network, if you spend $2 million in buying a better network, it will not serve anything. It will not be useful. Okay. And this leads us to the efficiency model. Okay. You have seen this a gazillion times by now, so I will just fast forward it. We also compute the pop metrics, okay, the same tree. We are able to split the serialization and transfer for the communication efficiency. But I wanted to show you where do we get these factors from. It's not black magic. So imagine this situation. We have 2 iterations and 2 MPI runs. Okay, and the first process has less work to do, so less blue, than the other one. Because it has less work, it reaches the MPI send earlier. Okay, and this MPI send is stalling because the receiver is not ready. Only when the receiver reaches this point, the MPI send actually can start the communication. Okay, and this behavior repeats. So what we do is to collapse all the computations on one side and all the communications in the other. Okay, if you do that and take a statistic, you will see that we spend 50% of time in MPI. So we blame in MPI because the MPI implementation sucks because we are spending a lot of time in there. And that is not true, because this part in MPI cannot be blamed to MPI. It is blamed to the imbalance. So these are the 2 factors that we are trying to measure. One is load balance, that measures what is the difference in blue, And the other one is the communication, which measures what is the common time that everybody spends in MPI, not due to the global imbalances. And so the product of these two is the parallel efficiency. Here you have a quick recap of what this means. But the important point is that you can measure these numbers directly in Paraver over a profile of computing time. And why is that? Because if you pay attention to the formulas, everything is computed based on the blue. So just by having a profile of the computing time, you can get these numbers. And then there is a refinement to this, where we can split the communication efficiency into the other two factors. Okay, imagine this other situation. Now we have the same two MPI ranks, but the imbalance changes in each iteration. Now the process that has less work in the first iteration is the first one, and in the second one is the other one. When we do the same trick of collapsing computation and communication, we get this. In this case, the global load balance is perfect now. And again, we have 50% of time in MPI, but this part cannot be attributed to MPI because it corresponds to these imbalances over here that are changing in every iteration. And this is what we measure with serialization and transfer. Serialization is measuring these dependencies, and transfer is measuring the real transference time. How do we get this? With MMS. With MMS, we simulate the ideal network. Okay, and because in an ideal network, the real transference should go away, the red goes away. Okay, so the simulated trace looks like this. And any remaining time in MPI in the simulated trace is serialization only. Okay, so with that, we can split communication in these two factors. Again, you have here a quick recap of those. And the takeaway is that you can measure this directly in Paraver over the real and the simulated trace. Okay, and directly with basic analysis, because basic analysis takes the real trace and internally simulates it. One last example about how to use the model is this scaling test of CGPOP. Okay, this is ocean modeling application, and it is an intrinsically unbalanced problem because you take the Earth, you split it in chunks, and then the amount of water per chunk is not balanced. Okay, so depending on the chunk, you have more or less work to do. But then we do the scaling, and the scaling was perfect, at least in this range up to 400 processes. But then we look at the efficiency numbers, okay, so because we think we are happy, but maybe we are just lucky here. We look at the efficiency numbers, and we see that this parallel efficiency is the dark blue line, starts at 80%, below 80%, and keeps going down. And this is mainly due to this purple line, which is the transfer efficiency, which is going down, okay, quite drastically. When we look at the other part of the model, at the computational scalability metrics, what we see is that there is one which is skyrocketing up, and this is the IPC. The IPC is improving as we scale. And this improvement is hiding the fact that transfer is going down. Why this happens? Because this was a strong scaling, so when you increase the number of processes, the amount of work per process is proportionally smaller. So things start to fit in cache, and this makes you not to have so many cache misses. So performance improves, IPC goes up. And so this is compensating for that loss. And this is why the scaling looks perfect. But then the IPC will not improve forever. It will hit a ceiling. And when this happens, transfer efficiency will continue to drop, and this will not scale anymore. Now, this part of the presentation, I'm saving it for tomorrow. The idea here is to show you other tools and other techniques that we developed to gain further insight from the data with more abstract views, overviews of the whole application. But we save that for tomorrow. We will just fast forward it so that you can see the pictures and you think very interesting. Okay, very nice for tomorrow. And I just wanted to give you a couple of ideas of our philosophy or methodology. The tools that we develop are not automatic. They don't have a magic button that you press it and fix me everything, optimize the application. No, it doesn't work like that. These tools are meant to help you in thinking, in formulating and validating hypotheses. So you look at the application, what happens here, it doesn't work as expected, what could that be? The reason for that. I think it's a problem of unbalancing the computation. So typically this happens because working balance. Can I verify this? Yes. How? With instructions. So the tool will help you formulate questions and validate these questions. The other idea is that we try to go beyond the raw numbers and provide you with patterns, with shapes, with images that expose a structure that help you understand better what is going on. There happens to be an XKCD comic for everything. Then starting with the tools can be a bit daunting at first. You were introduced to the POP methodology, where you first try to identify general structures, select areas of interest, and then when you have found one, you have a look at the efficiency metrics, and depending on what they tell you, you can target a more detailed analysis, okay? And the questions that you can ask yourself in many cases are the same. So if you see that there is a problem of load balance, this is the examples that we have been seeing, okay? Is it programmer's fault because the work was not well balanced? You can check that with instructions. Is it the system's fault because it cannot deliver constant performance? You can check that with IPC. If you see a problem with IPC, you can check architectural counters to see which part of the pipeline is limiting you. You see low serialization. This typically has to do with dependency chain. So you can have a look at the sequence of MPI calls. You can have a look to see if there is noise that is perturbing randomly some processes and triggering these dependency chains. You see a problem of transfer. You can evaluate with DMMAS whether it is a problem of bandwidth or latency. Okay, so these are common questions that can help you get started. One good thing is that Paraver comes with embedded tutorials, okay? And these tutorials can be applied to the trace that you are looking at, to any trace. And in this tutorial, this methodology is explained and you follow step by step. It suggests you views to look at and it gives you explanations on how to interpret these views. So this can help you to get started. And then my final slide. So you can get the tools from our website. They are open source. There's a lot of documentation. You can reach us at this mail if you find any issue. And in the hands-on, you will see that how we use these tutorials. So the takeaway, it is very important that we understand how the applications behave, and for that we need to ask questions. Use visual tools because they take advantage of this power of your brain to process visual data. And I've shown you examples where the devil was in the very low level hidden details. So try to dig down until you find them. And do not over theorize about your code. No, I think everything is perfect, or I think my problem is that. Look at it. Look at it because sometimes you find surprises. And that's all on my side. If you have any question, please shoot. And now we move to the hands-on session where we will get traces and start analyzing.
Couple of them. Don't worry about that. So, okay. No. No. Okay. No. I will introduce Extrae. So Extrae is the tool that helps to actually captures the data that then is fed to Paraver to do the performance analysis. Extrae works with production binaries. You don't need to recompile, relink, or do anything to them, and it captures a lot of information without doing that. Of course, you can also add use the Extrae API to add some instrumentation by your own, but of course you will need to recompile if you use the API. The recommended way to use Extrae is through LD preload. It works in most POSIX systems, and as I said, is the recommended way, but it also works with DYNINS, function instrumentation, if I'm not wrong. And as I said, there are the alternative with the API. I'm going fast forward. So to use Extrae, first of all, you need to connect to the machine. In this case, it will be the accelerated partition of Mare Nostrum, because we will get MPI, MPI plus OpenMP, and MPI plus CUDA traces. The MPI plus CUDA you will get this later, but tomorrow. But we will use the same machine to do so. So use your user, the provided user. I think Marta gave the users to you on the first day. So use it to connect to Mare Nostrum accelerated partition, and you will see that Extrae and the other tools from BSC are available using modules. So it's a convenient way to use them. Now I want you to copy one of the folders with the prepared materials. It's in GPF. No, it doesn't work. The puntero.
Está la pantalla.
Okay.
No, es que no se refleja en esta
Yeah. So you'll need to go to GPFS Scratch and CT362, which I think you have access to. And there you will find the folder BSC tools with the materials we will use in today's training. This afternoon or tomorrow, early in the morning, I will update with the materials for tomorrow. So BSC tool contains some folders with the materials for. So if you can do this, it should be fast. Oh no, contains some traces. Maybe it's not that fast, but shout when you're done. Shall I go on? Okay. So getting a trace. So it's easy as 1, 2, 3. So you need to adapt your job script, the usual job script you use to submit your application to the queues, configure what to trace, and run it. So it's pretty easy. If you want further reference on how to use Extrae, we have an online guide, and it's also available with the Extrae installation as PDF, I think. So this is the standard learn script where you request resources. I don't know why I'm using this. Because I cannot point it anywhere. Request resources. We load the modules. In this case, we will load GCC, and there's an I missing here.
Yeah.
So it's OpenMPI, not OpenMP. And we launch the application. We use Lulesh, which is a complete. We know this mini app well, so it's convenient for the trainings. And run the program. With this, you won't get a trace. With this, you will run your application, and that's it. To get a trace, we need to modify the job script a bit. In the folder you already copied, it's already modified. First, we will need the constraint perf paranoid, so we have access to hardware counters. Then we will give the trace a name, the output name of the trace. This is optional, but we will use it. And we will prepend this small helper script trace.sh to the binary. Please don't prepend this helper script before the MPI run or as run, because in this case it will not work. It will try to capture information from the MPI launcher, and it doesn't work. So prepend it to the binary, not to the launcher, not to the MPI launcher. And what does this small script contain? So it configures Extrae. It loads the module load Extrae. It says where to look for the configuration, in this case the Extrae XML file, which library to use. We will use one that only captures MPI information. So with MPI trace, you find whole list in the lib folder in the Extrae installation, and we run the program. This is very important. If you don't touch this, your program will not run. So don't forget the dollar stuff. So this is a very small table of some of the libraries you can find and combinations of the libraries that Extrae provides. So we have a sequential trace, an MPI trace, an OpenMP trace, pthread, CUDA, and combinations of them. So if you want to trace MPI plus CUDA, we have a library for that. As I said, you can find all of them inside the lib folder in the Extrae installation. The XML. The XML configures with the capabilities of the library we are using what has to be active, what has to be enabled, what has to capture. So we're using the MPI library. We want to capture MPI. This block, as we are not capturing OpenMP, we can forget it. So we want the color. So we want to know where MPI is called to pinpoint to the code where things are happening. And we want counters. Hardware counters, as I said, we need the constraint per parent option. And we have to select which ones we want. We want instruction cycles, data cache misses, total cache misses, resource stalls, many of them. We use PAPI for that. It's an intermediate library installed in my. I don't know if it's installed or we installed it. Both. So we can check which counters are available on the machine. And with this simple tool, PAPI set, we can select. You can select some of them and feed them here, and it will output what you have to insert in this part of the XML. The omnipresent flag argument will put all the counters after it in all the sets, and the rest will be on one set or the other. Then we have to select a buffer size, which is a compromise between the memory requirements of the applications and how many times we want to flash to disk, ideally only at the end of the application. We can also enable sampling, which will enable periodic data gathering. We will not enable that. And if we want to generate the final output trace, which by default it's set to yes. So we'll get the PRV file, which will be open with Paraver. So after this quick introduction, you can go into the first of the example, which is inside BSC tools Extrae MPI, and use this command to launch the script to the queues. And after 1 minute, you will get the Paraver trace. You can check with ls if you have these 3 files. If not, they are also generated under the traces folder, which you can copy, and you will have it. I'll wait 2 minutes or something like that. Okay. Okay. If you submitted the job to the queues, we'll wait and we will install Paraver into our computers. Okay. So we can now download Paraver from the tools website, tool.bsc.es/downloads. And we'll choose one of the binaries, available binaries here, depending on if you have Windows, Mac, or Linux. And wait. And installing Paraver, it's easy. You just need to uncompress. If you, this is optional, renaming the folder, but I will use the renamed folder always. And run Paraver. By default, an empty window shows. And the next step will be to download the tutorials. To do so, we will click on Help Tutorials. If you need me to stop for a minute, I can stop. And by default, the tutorial window says that it cannot find any tutorial. This is normal if it's the first installation. But there's a convenient way. There's a button here at the bottom. I think it's a downwards arrow or something like that. And you can download and install tutorials easily using this button. For this hands-on, we will only need tutorial number 3. Select it and click on OK, and it will automatically download it and install it. There's also a manual way to do so, but I will not go through that. So, analyzing an MPI trace with Paraver, which is using Paraver. First thing to do, copy the trace into our laptops with SCP. And in the meantime, I will open Paraver and I will do the things. Open Paraver and load the.
Did you get that tutorial?
Yeah, so let me go back a bit.
Yeah.
So by default, if you click, there's a small button. If you click on Help Tutorials, this window should appear, and there's a small button, green button with a downwards arrow.
Yeah.
Yeah,
And then I check.
the number 3, introduction to.
Yeah. Yeah. Good.
Manual. So you have the trace
Just
in your laptop. And copy it with SCP. No son compatibles los números.
Pero las librerías y el MPI, las bases no me generado.
Okay.
Sí.
Está abierta. Está abierta, ¿no?
No estaba sellado.
Pero no estaba usado.
Ah, ¿has estado tú?
Sí.
Vale. No, no, sí, es igual.
Sí, sí.
No sabía si era de la otra día. And after loading the trace, we will open tutorial number 3. Sorry. So the tutorial number 3 walks you through an MPI, a simple MPI analysis. We will use this as a starting point. So the first thing to do will be to click on the MPI stats link, and it will open a Paraver profile. As Herman said, these are statistics. And if we will look at the outside MPI, which is when we are not communicating, we'll have at the bottom the pop efficiency. So average will be the parallel efficiency, maximum would be the communication efficiency, and average divided by maximum would be the load balance. So it's important to notice that Paraver by default doesn't zoom anywhere. So this is not our focus of analysis. This is the whole trace. Maybe the first thing to do would be to click on this open control window button here at the top left of the profile, which opens the timeline that generated this profile. In the timeline, we see the different iterations that our application did. And we can zoom by clicking and dragging from the end of the first all reviews to the end of the last all reviews, for example, and it will be our focus of analysis. Then these statistics will not by default update automatically. We need to right click on the timeline, copy, right click on the profile and paste the time. If we do that, the statistics are updated. Okay, now the average, the maximum, the load balance changed a bit. So as parallel efficiency, we have around 81.40%. Maybe your numbers are not really those numbers, but they should be close. So the maximum, which is the communication efficiency, it's around 95%. This means that somebody is computing 95% of the time. So the communications of this guy only take 5% of the time. So ideally, everyone should be able to do this like this guy does, right? And the load balance, which is the division of these two numbers. And from communication and from load balance, we see that the problem in this application is load balance, which is the smaller number, right? So let's check how the balance of this application is. To do this, we'll click on the second link, which is the useful duration, which shows the durations of the computation, the bins of duration of computation, and ideally we want to see straight lines here. So we want every process to do the same, to take the same amount of time. So we want to see straight line here, which is not what we see. As a reminder, it's convenient to always copy and paste the time, so we always focus on our region of interest. In this case, initializations and finalizations are small, so more or less the image is the same. But we already see some imbalance here. We see two distinct blocks here, one large block here and one smaller block here. The computations of this block are taking longer than the computation in this block, and we see a zigzag here, right? Some clouds of zigzagging. So we also see this blocky structure here a bit. So this is unbalanced in two ways, right? This blocky one and this zigzagging. This blocky one it's interesting because the first 40 processes are taking longer than the 24 remaining processes. This is a 64 process run. The Mare Nostrum accelerated partition has 2 sockets of 40 cores each. So this is indicating something, right? So maybe one of the sockets is completely filled and the other one is not, and this is generating this imbalance. So why don't we check that? We can check that with Paraver. We open the hints resources process mapping, and we have the process mapping here. And well, this is not an easy photo to see, an easy image to see, but I will help to do. So we have threads on the y-axis and cores in the x-axis. So as I said, the accelerated partition of Mare Nostrum 5 has 2 sockets of 40 cores each. So from 1 to 40 is the first socket. From 41 to it ends at 74 because we're not using the many processes, is the second socket. So we can draw a line at 40, which is here, right? Value 40. I don't know why it doesn't work, but we can draw a line here. And it is not painting. I don't know why. What is happening? Why? Come on. Sorry. I don't know what happens to my laptop today, but it's not painting. Okay. Can I paint into Zoom? I don't know.
Sí,
Ah, yeah.
de allà baix tens Ai.
No. Ah, pues el teu, per això. Ok. I pots fer línies rectes en Zoom o no? O és...
Sí, sí, eso.
So, so here, more or less, will be the division of the 2 sockets. Do you see the line? Okay, so we can count, but I already did that for you. It's balanced, okay? So we have 32 and 32 processes on each core. So what is happening? I already know that, but I will show you. So for this, we will have to look at how the accelerated partition is structured. So we have 2 sockets, but these 2 sockets have 2 NUMA nodes. And each NUMA node is of 20 cores. So what is happening here is that, let me go back to, and the painting is gone. Yeah. So let me draw a line here again. What is happening here is that the first 20, which is around here, I think. No sé cómo va esto. Around here. Ah, només puc fer una línia?
No, pero deixa anar, ets pinta, no?
No, mira.
Oh.
Y ahora sí pinto. Aquí.
Okay, sorry for that, for the ones online. I think we are back.
Here is example in the slide, so mention this here. So this would be the drawing I intended to do. Okay. So we have a Luma node that is completely full and the other that is half empty. Okay. Ideally, we will generate a second balance trace by adding. We have to do this manually in a Slurm. And we will get this with 16 processes per Numa node. Okay. I need to go fast because we don't have time. So, and you can do that if you want in the break or in the afternoon. We can do that. Okay. And the runtime is down by 0.4 seconds, which is not much, but it's a 3-second execution, so it's a lot. And the efficiencies went up from 81.5 to 87, the parallel efficiency, and the load balance improved from 96 to 91. So just by doing this, we got an improvement, right? Then there is the second unbalancing, which is this one. That this one is not created by the mapping of the processes, but is generated. If you we click on the third link, it's generated by unbalancing instructions, and we can check that here. Again, copy and paste time. So we zoom into our focus of analysis. This would be the block unbalanced region, which in instruction is completely balanced. But we have this zigzag here, which maps pretty close to what we see here. Okay, we can check where this happens. We can use this this magnifying glass here, which reads open filter control window. Check where this happens. It happens everywhere. Okay, all the iterations. So it's a repeating pattern. Why is it moving? Okay. And finally, we don't have many time. I will show you how to check where this behavior happens in the code by using colors. To do this, we'll click in hints, call stack references, color function. Okay, copy and paste the time as always. There's another more convenient tool in Paraver which synchronizes windows. So this is convenient because with just one button, every window you want to look at it's zoomed in the same place. So to better read where everything happens, we will zoom in one of the iterations, which is this. Copy and paste the time again. And in here we see the colors. This is the main, and here we have the consent. These are functions, consent functions. The consent, if you want to check the colors, you can double click in one of the color. You can go to colors, make the window a bit bigger. If I can, yeah. And here you have every function around the unbalanced region, right? And I don't know, I have to finish or I have some time.
You have 5 more minutes because they were setting up the coffee.
Okay. Well, now if you did an analysis that you like in Paraver, you can say, hey, I want to save that for later. Paraver provides two kinds of methods. So the first one is to save the session. If you save the session name, okay, it saves everything. So when you open Paraver again, you can load the session, and everything will open as you had. So as it were. So every window will be the same positions and everything. The second way is to say, hey, I generated a view that I really like. I want to save that to use it, be it in this trace or on another trace, because I'm seeing something that I think it's interesting for my analysis, for my future analysis. So you can click on right-click on a timeline or in a window and click on Save Configuration. You can give it a name, fancy view. Save it wherever you want. I will save in the desktop. Save. And I can open it in a subsequent analysis. I can go to Load Configuration Desktop, or as I saved it recently, it will be in my previous configurations. I have it here, fancy view, and the same window opens. I can do this for all of the windows, for different windows in my session. To do this, from the main window, I click on File, Save Configuration, and I select everything I want to save. I want to save, I don't know, the colors, MPI color, and the profiler of MPI. So I want to save these two windows. I click on OK. Fancy view 2. And in a subsequent analysis, I have this fancy view 2 configuration file, which opens the two windows I saved. Okay, that's it. There's more in the slides, but it's 10:30. I don't know. I think that I do have everything. Ideally, we would have to obtain an MPI plus OpenMP trace and look at it. If you want, you can do that. It's easy. It's just doing it, but we will do it tomorrow. We will have some more time, but getting the trace is easy. The analysis is another thing. So thank you and sorry for everything that happened. But it's the...
And they also have more time this afternoon.
Yeah. In this afternoon, if you need anything, we'll be here. Sí, por eso creo que me he saltado todo. So if you have any question, you can ask.
Also make a module available on Scorpio and find out what is required when trying to load them. We have basically the compiler and the OpenMPI, which are these two. And we have Scorpio and PAPI as required for measurement. For the post-processing, we also need kubelib, which is part of our kube tools. And I'm just loading right now also the Scalaska module, because this is essentially the complete environment for Scorpio and Scalaska on the GPP partition. Also, we are not using Scalaska today. And we have seen the BT example before, so here's a link to the official site, but we just can go to the projects directory. I'm going to my user folder. And I'm entering the Scorpio exercises, which are in the exercises folder. And if you're getting into that, you're seeing two folders, which are the two examples we're using today and tomorrow. Today we're going for the BTMZ. Tomorrow we also will use TLIF CUDA, which is basically MPI plus CUDA and some remainders of OpenMP. So inside the BTMZ, it's a complete benchmark suite. So with various benchmarks, we are just using BZBT. Similar to what Tarek, for example, showed you yesterday, we are looking at the config make dev, which is when it's loading. Basically the setup. The only line that is really interesting for us now is the MPI F77, which is telling you a lot about the age of the benchmark. And we are using GCC, and with this GCC, we also need the fallow argument mismatch because the older written code produces otherwise errors. And we also already put in the prep variable, which we are using for the instrumentation at a later point. But you don't actually need to change anything that's already prepped. Just for reference, if you want to change a compiler or use it with a different tool chain, you might need to change the compiler there. So for the uninstrumented reference, you write the BTMZ class D and nprox 32. This is essentially doing the same as we did before, and this should result in a binary folder bin where we have the binary compiled for 32 processes. This is a slightly older version, I think, since the versions that Celtic used, it still uses fixed process numbers that you have to compile in. But since we're only using one case, it doesn't really matter. So you can scale up the benchmark classes, and they are doing increase quite strongly the computation duration. This is basically chosen to run roughly a minute in uninstrumented case for 2 nodes that are completely loaded. And if we are looking now at what we want to do, there are prepared job scripts. If we are looking down and one folder and then job script, and then go to Mare Nostrum 5 and copy the runs slum now here. And have a look at it. It's similar what the others basically used. We're using 32 tasks with total processes, 16 per node, and times 7, which is an odd number, literally. But that's the way to get to the 112 cores, basically. Not necessarily always recommended to use every core, because we have MPI under the runtimes create threads. So having a few cores left on your node is also sometimes helpful. They're using the account for the NCT 362 and use the QP training queue. Here is a recommended slot setting for among awesome you have to, in our newer Slurm versions, explicitly say these CPUs per task so that they are binding correctly. And otherwise, we are just specifying the case and can run it like this. That's in the hopes that it starts at some point. Since we are already kind of expecting what should be the outcome of that, since we have seen that yesterday before, I think no one should have a problem in getting to that point, and we can Now it's running. Wait until it's done. The next step would be then to instrument our application, which would be doing the same compilation step. We're going one step down, but instead of let me make clean so that all the objects are gone, and then we define the prep variable we introduced into the config mix file, and prefix everything with score P. This is the basic principle of our instrumentation, the score P, that every compilation line is prefixed with score P. In some cases, adding that to make files is a bit complicated, or particularly when you're using CMake or other build systems. For this, we also have compiler wrappers. So for the MPI-CC, we have a score P-MPI-CC, which basically combines the prefix and the compiler command, and then continues with all the remaining options. This is to avoid the explicit prefixing, which is inconvenient in some cases. So basically, the compilation itself looks like the same. I'm just checking how our job is doing. It's done. So now we can check the output file. And as before, we have the C224 total number of threads in 32 processes, and you ran with 62 seconds of runtime. That is our reference number. One nice thing about the benchmarks as a use case is usually they have a own time measurement in it for at least the total wall clock time. So this time this is nice to use when, but you can also time the measurement itself with easy methods, because you want to know how long your uninstrumented run would work in the comparison. So now that we also have our instrumented executable, we will find it in bin.scorep. Sorry, I did a. Now, aside from the bin, we also have a bin scorep. And it's the same executable, just if you're looking at now at, for example, with LDD, you get, aside from the classic dependencies like the Fortran, GOMP, etc., you now also get these the adapters and these Scorpio libraries, which are linked to the binary. It's a good way if you're not sure if your instrumentation went fine to check with LDD, because there should be all the binaries listed. And the next step in our is now basically to run the measurement with score P. And for that, we copy the next job script from the Mare Nostrum folder, which is named score P. So that was a bit too much. And if you have a look at scorep.slurm, which is essentially the same with an exception. We have a block of measurement configuration. Mostly for the first measurement, we are only setting the experiment directory, because that's the name for where the results are placed. If you don't set it, you get a generic name with a timestamp, which is far more difficult to distinguish from using for later use. Otherwise, we have some other variables we are going to use later, but all the run command and the overall settings are the same. And with that, we basically can SBatch and this one. And just if you're wondering, in the lower left corner, I put the slide with the setting for the environments in case you are missed that. If I'm going too fast or if you have any question, please speak up. We have time, and right now we are just waiting anyway for the, which we expect to take notably longer, so we have to see. But did you everyone get to this point? Did you run into issues?
Yes.
While we're waiting, we can look a bit at, as we saw, we configure our SCORP measurement with environment variables. And if you want to know what environment variables to use or what are available in this specific configuration of SCORP, you can use the command SCORP info config vars and there's a -- full for good measure. And we see the full list of environment variables that are available, and you get a short description, you get the default values. So for example, by default, we are doing just profiling, and tracing has to be enabled manually. Because generally you want to do a profile first to see what you get to expect from a trace measurement in terms of size, and to refine it first. So that's our default setting. And there are various other settings we might or might not come across. One very common one is the SCORP total memory, which we have to adapt for tracing because the 16 MB from the default value is mainly usable for profiling itself, while when you start tracing, you will need more memory. And just to preface this, we are setting memory because SCORP is allocating memory beforehand in an own memory space, and with a maximum of 4 gigabytes, and anything goes above that, we cannot handle. And generally speaking, even if you are just below the 4 gigabyte mark, you really have to refine your measurement a bit more, because with exceptions of very long runs, you shouldn't get many of faults in most cases. And the various options vary depending on which paradigms are configured. In this case, we are on CPU-only installation, but if you are on the ACC partition, for example, you are also getting the settings for CUDA, OpenICC or OpenCL, depending on what platform you're on. So let's see how far we got. Our job is through. So now we have the name, the folder with the result and the name you're choosing. And the first thing we want to check how long it took. And with the same settings, we are going for 134 seconds, which is more than double the time of the uninstrumented run, which is bad, to say the least. The problem with overhead is to some degree, it's unavoidable, but it's also often hard to estimate how big the influence of your overhead is. So if it's evenly distributed, you can get away with way more overhead than if it's unevenly distributed between processes for some reason, and it's hard to tell beforehand, so reducing it is the first goal to do. Otherwise, in the result folder, we can have a look for now what we are getting here. And we are essentially getting the profile file. That's the config used, which is which contains all the all the values used, also the default values. So it's not just the values you are set, and a manifest file. The manifest file is basically for user purposes as part of the documentation of the run. You're getting a list of elements you should see in the run. In particular, if you have an error and abort early, you should still see what you should be getting. In this case, the manifest is just the description, the copy file, and from this profiling system, we are getting the profile.qx. And it also lists the variables you set during the in the environment itself, and which in this case is just this copy experiment directory. So in principle, we now have a measurement that we could look at, but the interesting question is how good is this measurement, and we should personally we should improve it before going further and actually looking at it. So the next step is basically scoring and filtering. This is a step that tells you how expensive these various regions are and how much extra overhead you're producing in terms of time and in terms of buffer space. To note, the time overhead is generally constant for every region enter and exit we have. So independent if you spend 10 seconds in a region or if just 1 millisecond, the time overhead is the same. But of course, the percentage of that overhead compared to the time you spend in the whole region is different, which makes small regions very costly in this sense. And also, if you have very many instances of small instances, you're also generating more events that increase the trace buffer size. So both elements are to be considered, while the time overhead is relevant both for profiling as well as tracing, while the buffer size and the trace size is only relevant for the tracing measurements. And the process of scoring and filtering we should do as long as we have too much overhead and until we're ready to go further with this measurement. So for this, we have a tool that is called Scopy Score. And if you're looking now on the result we got, Scopy Score on the Scopy-BTMZ, and then on the profile, we are getting some information. Essentially, 2 blocks. The first block estimates the trace size, which is 3 terabytes for a 2-node job, which is not something that we really want, and with 105 gigabytes per process, which is a lot. That's basically the scope, the total memory, which we should be setting when we wanted it to use as is, to avoid additional buffer flushes during the measurements. But since we only can go up to 4G, we don't really want to do that. And the block below shows you how these memory requirements are basically calculated and split up. Overall, we have the 105 gigabytes, which is max buffer size. Max buffer size means that this is the maximum which one process would have for a very symmetric program. That's essentially the same over all processes, but if you have very asymmetric executions, that might differ between different processes, and so the maximum is set here. You have classic paradigms like OpenMP and MPI, which are basically functions and regions that are covered by these paradigms. Then user is basically user code. This comes from compiler instrumentation, so that's your function enter exits. And there is combined. Combined is technically also user code, but its only difference to user functions are that they're on the path to another paradigm like OpenMP or MPI. Like this small graph on the left side here. The point of a call tree and a call passes in our result measurements is that you can distinguish different MPI calls. If you have multiple MPI sends on different paths, you can give context with a call path until this point. And if you are starting to filter out paths on these call paths, then you're losing context. So you're losing a level of detail when you want to distinguish different MPI calls, different OpenMP calls, different OpenMP regions, because they are happening on the same level. In an extreme case, you basically could filter everything but main, and then every MPI sent would be an instant in this on this level of execution. So the primary target for our filtering, where we don't really care that much about the context if you're just on user functions, and only then if you're looking at functions that you know what they're roughly doing and that are too expensive for what they are bringing in level of information, basically. To get on the level of regions, you can go with this copy score again, but add option of -R, which lists on a region by region breakdown. It's easier to look at something like less, which gets you essentially the top part you got before, but also then the block of functions of every region that is recorded in the profile, sorted by the max buffer size. And we see that the top 6 functions here are basically the majority of the 105 gigabyte per process we would be getting. And these are functions, although if you're looking at the columns, so we have the max buffer, which is the requirements, which is really a product of the number of visits times the amount of memory required per visit. They spend a whole lot of time, but only 0.11 microseconds per visit, which is very short time. So we have here a lot of very short function calls that don't really contribute too much to the expressiveness of your measurement, but cause a lot of the measurement overhead. This is a Fortran program, so this is not even a bad case. If you have C++ with very small template functions, getter functions, setting functions that do 1 or 2 steps in one call, that's basically no time spent per visit. And these are functions you want to easily filter out to reduce the over requirements of the memory. And just to be clear, filtering means that the time is not lost, the time is just attributed to the parent. You're losing a bit of level of detail, but not the whole information. So the next step would be how to generate a filter file so that these are not included. To improve the user experience, we added an option to generate a filter file with Scopy score. Which is with the option -G. This uses a few parameters with an heuristic to estimate which are useful functions to filter, and then generates a file called initial Scopy filter. It produces also a bit of text how it's to be used in a measurement. So we have a variable we saw in the Scopy info output, Scopy filtering file, which would then be set to the initial Scopy filter file. You also have the option for some compilers to do compile time instrumentation during the instrumentation step, which has the advantage that the overhead is reduced again, because even if you're filtering on runtime, you have some if checks if a function is filtered that still have some minor overhead. If you have enough visits, you're still getting some overhead. But first, we're looking just at the runtime filtering. Generally speaking, even if you go the route of compile time filtering, that is the last step. First, refine your filter file to the degree you're comfortable with, and then use one step to compile time filter. Now we want to see just how good our filter is. Also, if you're now I should have the initial Scopy filter file. Let's see what the effect of this filter would be without actually rerunning our measurements. So we are doing a Scopy score. Now with the option -f initial filter file. We are doing also -r for all the regions. And again, we are using our profile from before. Now we are essentially getting a preview of what this filtering would do during our next measurement. And we see in the top, the aggregated information is just 90 gigabytes of trace size, which is better than 3 terabytes for sure. But and it would technically also fit with a bit under 3 gigabyte into the total memory, but it's not yet in a nice way for such a short and refined benchmark. And we want to find out why. We see in this tabular now that we have the column filtered on the left side, and plus means it's filtered. That's the summary amount of what's already filtered out, which is quite a number. And minus is where nothing happened, and the star is for where mixed elements sind. And if we are looking at the region breakdown, we are noticing, oh yeah, the generation produced a filter that just filtered the first 3 out and not the second 3 we actually also want to filter. And the reason is the default heuristics are so that for one, the last column here, time per visit, should be below 1 microsecond. And the filter, the to be filtered region should have at least 1% of the total trace buffer requirements. And this is just to say, okay, this is a relevant function that makes sense to filter, because yes, you can filter everything which is very small, but if it doesn't have a huge impact on your measurement, you may want to leave it in just if you want to see it in your call tree, because it's part of your program. But these heuristics don't work for every case. So we have to refine our filter. And I left this in there by intention because, yes, you can generate a filter, but you usually have to still modify it to the extent that you really want what you want to see. And you have to check if the filter you're generating actually does what you want. You have multiple variants now to change it. One would be to modify the generation option. If you're looking for, by example, at Scopy -help, Scopy score -help, you can set options for the generation, and you have a buffer %, buffer absolute, visits, time per visits, and type that you can set to various effect to get a different output. The default is basically what I mentioned, the buffer %1 and the time per visit 1, and also that by default only the user functions are filtered. Yes, you can change that and try different if it includes the ones you want to do, but in particular in this case, it's easier to just do the manual step of looking at the filter file and changing it by hand. This is if you're looking at the initial filter file with VI or your editor of choice. You get first a bit of informational boilerplate, the reminder that you should look at it and change it to your needs. It also states the option with which it was generated, which is helpful. And then it lists in our syntax for filtering the functions with additional commentary basically used from the Scopy score output. And for the generation, we're using mangled names, which is prefixed with the mangled name. but you can also just use the demangled name. So we have a block of Scorpy names begin and then exclude a list of space separated. Can add here additional variables. So let's see. In principle, we can include hierarchically. So include everything, then exclude something, and then you can include something else. And in particular, with using wildcards, you can get into wild combinations. You also can, there's a mode Scorpy aside from region names, you can filter whole files, which is useful in particular if you're looking at something like C++, where you may want to filter out whole libraries like STL or something, and it's easier to do just by going to the whole file, and or if you have technically compiled with a library but are not really interested in the interna of this library, you also can do that with filtering whole files. In this case, we just want to add these manually. You can copy paste, or you can write them if you're. So, and as I said, they are just space separated. You have to be careful if you have demangled names. For example, with C++, they are full names with parameter lists. So you might have to need to use bash like wildcards to make sure that you don't accidentally split names so that are correctly matched. And if I now do the same check with the -f on the internet filter file, we are now getting to a total trace size of 4 gigabytes. It's just 140 MB of total memory per rank. And if you're looking down here now, we also have all of the 6 functions that we are looking for, that they are filtered. So now would be the step where we want to actually run this filter measurement. But before that, or just to make it sure that we are doing it in the same run and don't run too many times, when we add our Scorpy, edit our Scorpy.slurm, we also want to use PAPI counters. One thing we have to do for Mare Nostrum is to add the constraint perf paranoid. Otherwise, you're not getting any PAPI counters. That's also required if you want to actually look at PAPI avail, then you have to do that in an environment where that constraint is set. Otherwise, you are not getting anything. So we want to add that the same run. We just to be clean, we also change the name since it's our output file. Just and we are now setting our filter file. I'm uncommenting our variable, which is Scorpy filtering file, and we are, since we are starting in this folder, we can use the relative path of just initial Scorpy filter. And I also want to look at 2 metric counters. For these standards are basically, if you have PAPI installed and it's generally working, the total instructions and total cycles is something you basically always get. And as the last step, we want to also add the name. And if you want to look at the puppy counters, you can do here puppy avail. And you get a list of the possible puppy counters in the environment. And for our Scorpio configuration, we are using exactly the name used for the that you get from puppy avail for the counter names we are listing in our variables. Right now, since we are doing just profiling, we don't need to set anything with the measurement for memory. But before we want to do that, since we now added counters to the mix, we also added the amount of memory we require. And therefore, if we now look at our scoring result, we can refine this scoring result by adding a -c and 2. And this is basically to make sure that the counters are accounted for in the trace buffer size. And this adds two memory for two counters. I have to say, for two symmetric counters, which are called in every enter-exit, so that are predictable in the number of events they're causing. And we see we slightly increase the requirements to 311 MB per process. But again, this is for tracing itself, and but it's something we technically can already set for our settings, just to keep in mind. Given the amount of memory these days nodes have, taking 300 MB memory for each process isn't a huge amount. Particularly if you're looking tomorrow at GPU measurements, where the number of processes scales to the number of generally to the number of GPUs you're using. So these days you are not totally loading one node with just MPI processes, then this becomes an issue. So now we have modified our job script and can run it again. And the first thing we want to find out is how much is our time better than the unfiltered version. And let's see if that runs fast. I'm checking the slides if I forget anything. No, I don't want to spoil it. Any questions so far, or that should be relatively straightforward, but you never know. Now we're getting to the 1 minute mark. The job should hopefully, if I done. So now we have a new directory, a filtered file, and we can check the output file. And yes, we get back to the roughly 60 seconds, a few seconds more, but not noticeable. Otherwise, the run performance is basically the same, which is nice. And if we look at the new directory, we're getting one additional file, the copy filter, the new profile, and you have the same files otherwise. So the last step, after we basically got the result we wanted to, we are basically now at the stage where we can say, okay, this measurement should be usable and we can look at. And but the first or the last step before looking at it is a kind of manual step of cube remapping, which let's start it first. So this is a tool, Cube Remap, is from the CubeLib, which does some post-processing on our profile cubex and writes it into the summary output. The -d and -s are some options that go and pre-calculate some values that are implicitly inside the measurement itself for easier access. And the overall function of this remapping is to create metrics that are currently not measured. So it's structuring the measurement further. For example, the most prominent one is if you have a time metric, it is subdivided in a hierarchical tree and split into execution, computation time, OpenMP time, MPI time, etc. And generally, we consider only measurement complete once it's remapped. For easy examples, you can look at the raw profile, but it's usually more helpful to run the remapper first, which is a command line tool that is parallelized with threads on C++ side. Depending on the size and the system you're running on it, it can catch various amount of required hardware resources. It also does create some additional topologies that are now done in the cube remapper. And now we can basically go from here and go to the cube side of things and look at this result in detail. And just as an additional point, after the first run, we potentially could have looked at the first profile we got. It's technically possible, and depending on even with overhead, you can get if you're looking for specific information, you still can get them. But looking at them early has the disadvantage that it doesn't really help easily to find the overhead and reduce it, and it has the temptation of just staying with the first profile you are getting and before going through the adaptation step. Now that we are satisfied with this measurement, we are switching to the cube side of things. Let me switch the slides somewhere. So this is the first, it's the same as with SCORP. I basically start with a short presentation information, and then we switch to a demo basically from exactly the result we just got. So the cube tools, in particular the GUI side, which we see a screenshot on the right side, and you probably saw screenshots on Monday, maybe in some of the reports of the past POP analysis, is a parallel program for analysis report exploration, and it comes with the GUI and additional algebra utilities. The GUI side of things requires Qt5 or higher these days, and it was originally developed as part of the Scalaska toolset. Now it's separated in various components, the one the GUI side and one the command line tools. The main reason for that is that they have quite different requirements, and not all HPC systems allow really GUI execution on their non-logged-in nodes, or even if they allow it, it's not necessarily most efficient use of them. So keeping them separated has the advantage that we can install the library tools on the systems easily and keep the GUI side to where we actually need it. The latest release is quite fresh. It's from end of last year, and it has some improvements, in particular for the pop metrics we have seen before and for calculating them inside of Cube. The probably most interesting part right now is how to get it running on your systems. And similar to Macao or also with Paraver, you're going with a local client and using files remotely. For the local client, you have various options. You can install it from a table, which is for long-term use more, but the easiest option is running a binary. You can download Windows binary Mac DMG or a Linux binary app image. It's just downloading this from this link and executing it. Technically on Fedora, I think if anyone has that, so it's also in the package manager, but that's not the most common use. All the options you can download from this link here, scalaska.org, Scalaska Software Cube 4X download. And there's a section with the binaries. And on the other side, on how to access cube files. Okay, you can go always the manual way. The CubeX files are technically contained, so you can just copy the profile, the summary, over to your local file, or keep the entire SCOP directly for more context. But the solution I recommend is the one that also others used, is to use and mount that remote file system via VI-HPS. And basically, this is the command line you roughly have to use. You have to use the transfer node. I think the admins here prefer using transfer nodes for file transfers, but I think for our small users, you could also use the login node. And then mount, for example, the Scratch directory from the tutorial and to some random mounting folder you have on your system. That's the variant I plan to use. And I think I already did this or didn't. Basically the same line as my SSH config for this. And now I can go to and here I also have my app image, which I will be using later on. Now I want to leave this open. Also, another option that that you can try out if you want to at a later point is to we have a client server option for Cube. So you can run on the login node the Cube server simply without options if you loaded the kubelib already. The only thing you have to do, you have to do a bit of port mapping so that you get basically can collect through localhost to your login node. And for in particular for small examples, this should behave pretty similarly to using a local client on the SZFS. But it has the advantage if you're going big with files that you can use the hardware resources of a login node, which might exceed your laptop, to run a bigger cube file and only request the information that you're needing for specific views and calculations. So in the meantime, while you're doing that, I'm going for some principal information on the cube side. So the basic, there are two basic principles that I form the overall structure of cube, and that the first one is the representation of performance data as basically a three-dimensional space, where you have on the one hand the metric or property you're looking at, something like time, visits, etc., or bytes transferred. And then you have a call path location, so basically the code location where it's happening, the MPI send, a specific MPI send in your call tree, for example. And then you have a location on the system where it's running on. That's the threads, the processes, if you have GPUs, the GPUs, the contexts, the streams, and you get the hierarchy in the system tree. And you basically have three coupled browsers that display these three components in tandem, and you can select multiple elements and get from left to right basically to the result you're looking at. You also get the severities, the values you have seen for your different selections as a value, right, to the price for the precise comparison. But you get also color values from a color scale, and that help you quickly identify hotspots in your call trees or in the system tree, and pretty easy identification. And the second principle is that you're doing all three coupled browsers are tree browsers, so you have exclusive values that you can view via different modes to select the specific parts of your application at a detail grade you want to look at. So the principle of exclusive is if you have a function foo with a function bar inside it, the red part is the exclusive part for the function foo, while the function bar is separate. But if you're looking at the inclusive side, then everything below, basically in the tree of foo, is included in the inclusive values. These are the basic principles on which our navigation works. On top of that, there are various features we want to look at, but that will be due on our example we created. But here in the slide set, there is a demo with a T-leaf OpenMP that does basically the similar things and presents the effects for a case study that we did in the past. And that is usable as a reference for later when you want to look at these features again. So now we can do the load the, I already loaded. Right, so this is the, if you open your cube file locally without any file loaded, either you have a history of old files, or you can open also plugins that have meaning for that have no single one file associated. And since we want to open a file via VI-HPS, we are using Open. But if you would want to look at connect with a Cube server, you would use the Open URL case. But we want to look at this, and I'm now going to my mounted folder. So I'm going to use myself, the hands-on, the Scopy, the BTMZ, and now we are in the bin Scopy. So you have to navigate through your case, and the filtered Scopy was the last one, and the summary was the one we are remapped. And just as a reference, if you are looking at the file sizes, this is a factor 10 in it. So keep that in mind. If you are loading it, it might take a moment. And as long as the wheel is spinning, it should work. It's relatively fast. So the file system is playing along. So this is basically the default view you are getting when you're loading a cube file. All browsers are completely collapsed as far as they go. The call tree and the system, we have the metric tree on the left, the call tree in the middle, and the system tree on the right, as these are the defaults. And we have metrics on the left side. Metrics have different root nodes because they have different metrics, while the other have most of the time a single root node. And here also we see the effect of remapping, while the time, for example, would have been this singular node in the profile.cubex. In the remapped one, we have it, the substructure, and we are getting information like split into computation, MPI, OpenMP in this case, where we have the actual computation, then the overhead introduced from the different paradigms, mostly structured. It's something like management, communication, I/O, or request handling, or in the case for an OpenMP, we are going to get something like synchronization, etc. If we want to look at, for example, the simple as for example, the execution time, now we have to choose from left to right, basically, what we want to look at. And right now we are looking at the whole execution of the whole executable. And the first thing we might want to look at is the system tree. We can expand bit by bit, or for ease of use, we are call it expand all for now. It's small enough that we can do that. And we run it on the GPP partition. The naming is something we set during configure just to keep in mind for this configuration of Scopy. But we are getting various levels in this hierarchy. So we are getting different system prenodes. The machine is the base node basically, and then we're getting information from Slurm about switch levels, and then on the level of the nodes. This is basically the last system tree node we're getting from these Slurm information with the name of the node. And then we have the levels of ranks and threads in this case, where we have OpenMP. We have a master thread and 6 worker threads in this instance. And we, as mentioned before, we have always a number and a colored box that corresponds to the color scale here at the bottom, which is the default color, rainbow color scheme, but we have ways you can modify it in different ways. from the color selection, the distances between the different colors ranges, or going to a linear from one color to another, depending on your use case. But for most users, it's fine enough to use the standard color scale. And then we have basically here on the node side all the ranks listed top down in order of their registration per node and going down. Depending on the size of your measurements, this can be a quite large view. It might be not the most efficient way to look at this. We are staying on the system tree side. We are looking first, let's say, on the global information level. We spoke a lot in this week of various calculating the pop metrics, and we can do that inside Cube as well. It's calculated by default based on the models we are getting. So since we're in a hybrid case, we are using the hybrid calculations, and we're getting the parallel efficiency, load balance, and efficiency on the process level and the thread efficiencies. There are also categories for GPUs, but since we are not measuring GPUs at the time, they are not here. And we're getting information about instructions and IPC based on the counters we measured. The counters are added on the metric side as by name of the counter, perpetual instructions and cycles. Behind the metrics, we also see that we have different types of metrics, and in brackets is basically the unit we are calculating, and we have seconds for the time, we have occurrences for visits, bytes for transfers. Technically, the hash is that's basically just for number, because depending on your counter, it technically could be in different unit. So you can calculate the pop metrics basically for everything based with these counters. We have some information that will only be available in the trace analysis, the serialization and transfer efficiency in particular, that we might be seeing tomorrow in the Scholastica presentation. But we also can calculate, this is by default just for the total application. But if you want to look at a specific case, and we can know what our focus of analysis should be, and the benchmark, that's not that interesting. But going just by the Scholar chain, you can see that the solver is in the 80 subtree, and if we are can we recalculate basically for this subtree and have a selection not on specific start stop time settings like you would do in Extrae or Paraver, but on a selection in the core tree. You also can do various multiple selections and calculate all the values and metrics for that. To varying degree of if it helps or not depends on which selections you're making. This is a very high level view with calculating numbers, but we can also display the system view in other ways. You can use statistics, basically your standard box plot. Let's look at something which might be a bit more interesting than just a random number. And here, for example, if we are looking into the solver, we are seeing on the metric tree, the core tree, for example, the solver for y direction. We have a parallel selection, and if we are looking at the execution time, we have a wide range of execution time, standard box time, which we also can look at the violin plot, which indicates that we have multiple blocks of different categories for executions. The same we get for the implicit barrier, where we're waiting on the execution of the OpenMP do. If you want to look get a different view of that, you can also look at our topologies. The topologies is a feature that covers multiple sources of topologies. The standard topology that is basically just calculated from the system tree is the basically process times threads topology, which is an alternative display for the values where we just look at the color scale basically, and we can arrange the different dimensions. We have 3 dimensions here: node, process, and thread. Depending on your numbers per category, you can look at rearranging them in different combinations, or this is probably the best view for this combination. So we see our 2 nodes. We have 7 threads on the x-axis, and we have the 16 processes per node on this level. It's not looking at like much with all in blue. This is the reason, because all the values are very similar in on a high level, and look very similar in the scale of blue. That's because we're looking here at the absolute values, and this is a nice feature. Each of the columns we can also choose different representation methods. If you're looking per percent, you're looking at max range of percent, basically how much of the maximum you have in relative to your peers, in this case of your threads. And this is looking way more interesting for this case, because it shows you that the Paraver benchmark doesn't really work with all the 7 threads that well. You have, if you have the 2 regions here, we have the barrier, which is basically the waiting time in OpenMP, and you see that the last 3 threads on each process are doing heavy weightings there, or comparatively, given the representation method. You also see the complementary OpenMP loop, which is the relevant computation time. Does a similar thing, that the first threads are actually doing more work than the last 3 ones. So this is a nice view, which is an information which is technically also visible in the system tree, where you can see the similar color scheme across singular processes. But you might have to scroll through a lot of processes to actually see the pattern. With a topology view, basically have the ability to look at the whole system tree in one view without scrolling, which does help seeing patterns that are a visual representation of the communication behavior, or synchronization behavior in this case. You can get a similar view of all of the threads in the sunburst, which works for this case relatively nicely, which is presenting every thread on this level in the outermost circle, and you can select the ones below and go to the process level, and go more innermost level is the node level. So it's basically similar as the topology view. It allows you to see the whole system tree in a singular view, and you can go on different levels of detail with looking at these rings of threads and locations. It gets more difficult if you add GPUs to this, but for threading level, this is quite nice information. And but if you are going the numbers way, is also possible. These are the basics. I think for most people to get started, you're looking at look at the metrics. You can look at the time distribution over your different paradigms as a first view what your application is doing. We have an idle metric which is calculated, which basically shows you which threads do less, spend too much time doing nothing, which is similar to it's a relative value, and it's measured against the ball club time of the master thread. And these are informations that you can get started with. You have additional metrics which are already available in the profile, like you have bytes transferred, which is, in this case, if we are looking at which functions, this is in case MPI communication time, we are getting point to point. We have collective time and something like an MPI reduce, and can see these through the selection in the core tree or the selection in the system tree. And in this case, since the MPI communication happens only on the master threads, the only involved threads are the first threads of this view. If you want to go into more creative uses, I basically haven't used any of the menus here. Most are describing options to modify the usage that you can have here in your measurement. So you can, for example, change the color map, which allows you various amounts of influence on the how your numbers are distributed along colors. You can go into precision. You can modify the look and feel of the trees. You can change the dimension order. Right now we are looking at metric tree, core tree, and system tree, technically. And this order is the default one and the most used one. But if and the evaluation is from left to right. So the selection from the left side is applied through the core tree and to the system tree, which means that you have here the number is for the total computation. Then you have the computation time. Here is the total computation on this call path for every location. And then we have on the system tree, we have the value for the split in each rank. So the evaluation order matters, and you can change, for example, the dimension order to system, metric, and call, which changes the order. And this is maybe interesting if you're looking to know what a specific thread is doing. If it misbehaves or has a strange behavior, you can select first the thread, then the time, and then what this contribution to a certain core tree is. As I said, this is not the default view, and you can get into various behaviors there, but anyone starting, I would recommend staying with the call tree. We have also some additional information, like if you are having here selected a zone call, and we can go into the source code location. Since the file, I'm on the remote system, so the file is not in the location where it was originally compiled. But if we are going, if I'm here in the folder where the measurement was, I just have to go down to the bin score P and then the BTMZ, and then he finds the source code collection. So you can basically map your call tree to the location of in your source code and see what specifically caused that. It's in particular helpful if you're not that familiar with the code and finding out where you're going. There are some caveats that not always the file numbers are correctly presented, in particular if you're going with source-to-source compilation. Sometimes you are missing one, or some compilers doesn't provide the numbers correctly. Then you might be off there, but it's a nice feature to have. I'm not. What's the timeline? So we are nearing our end time for the session, and I think we have a nice overview about this general use for the cube file. It's to get you started. I would first look at the metrics and the pop advisor metrics to see where your issues are. Then looking at the metrics and the distribution of your execution codes, which is a nice way to go. And the next step would be then going into detail on certain elements that have high relevancy for your code. Let's see if I missed something on my presentation for Cube. I think I'm. Yeah, tomorrow we see that the post-processing with Cube remaps we did by hand. You also can do with Kalaska automatically, but that can we do tomorrow when we are looking at this plan. So as the last slide, I just want to show you basically the general information sources and contact information. As always, we are happy to receive any comments and also questions, problems, etc., which helps us to develop our tools and bring them forward. And I think this is a good point to stop. We are right on time, and I don't want to stop anyone from lunch. So
That's a good